Okay, exciting times ahead. We're leaving derivatives soon and going to antiderivatives, which means undoing the derivatives. Do you know what that's called? Integral. We're going to integrate soon. But first, to start, before we hit integral, we have to understand how to estimate under a curve. Because if we have a nice geometric shape, it's pretty easy to estimate. For instance, this rectangle right here, to determine the area of the rectangle, what are some processes you can go through? There's different ways you go about determining this area. What's one method? The area of the rectangle. And the area of the rectangle. Yeah, length times width. Okay, what's the width? 3, what's the length? 6, so area is length times width. Which is 6 times 3, which equals 18 units squared. This would be going another way to go about finding the same area. Ooh, I didn't even think about that one, but okay, there we go. Two triangles. Okay, half theta times height times by 2. That's another way. Okay, sure. Okay, what about not splitting the shape? Because we can go all day with that. Okay, good. That's what I want to again. Count all the squares. 1, 2, 3, 4. This is not what area is in units squared. And then how many squares do we end up having? 18. Okay, that's another alternative. That's a nice phrase to make a rectangle nice and squared. What if we have this oval over here? We're going to determine the area of this shaded region. Do we have, number one, do you know formula for area of an oval? Or an ellipse? No, we don't. Okay, we have some solid squares we could add up. 1, 2, 3, 4, 5. These are called another box. 6, 7, 8, 9, 10. Those are pretty solid, right? Is the area 10 units squared? No. Because we have some partial squares, right? We combine a couple of the partial squares together. Like maybe these two, if we put them together, would it almost be another square? With a good estimate. Let's see. If we combine this little piece with this piece, would that be like another square? What if we combine this little piece with this little piece? Would that be another square? This one's cool, actually. We can probably say that's 1, and this is 1. Those are pretty close to being relations in. And even like, we kind of combine all that. That's another one. This is another one. What's your approximate area that we're getting out of this? This is approximate. I'll take some of those answers. Because I haven't just, actually 117. Actually, well, we already have 12. And this is 13, 14, 15, 16, 17, and I still haven't used this one. I haven't used this one. I haven't used this one. Well, this is pretty close to 18, 19, approximately, you could say approximately 19, approximately 20, depending how you put them together. Units squared, can we all agree on that? Okay. Well, there's actually, down below, we have what function function look like? Right here, what does function does that look like? Square root function, right? We can approximate underneath the curve that it stops at the x-axis by using RAM approximation. Pretending like we're making rectangles. RAM stands for rectangular approximation method. Okay? These are called Riemann sums. I need Riemann is the one who came up with this. Riemann, two N's, sums. We're going to have a bunch of rectangles, because we can find the area of a rectangle, right? Length and width. And we're going to add them together, hence the sums. But we have three different ways we can do this. We can do it by a right rectangular approximation method, which would mean on a rectangle, we're going to be lining, oops, that's not the right side, let me try using that the right side. On a rectangle, we're going to be lining up the top right corner of the curve. We can also do a left rectangular approximation method, which would mean we'd be lining up the top left corner on the curve. Or, what's the third option you think? You've done right, you've done, what was your right, left, middle. Where we take the midpoint of the top and line that up with the curve. Okay, so in colored pencils, I'm going to do this first one in red. So take one of your colored pencils. And we also need to know the width of our rectangle. For today, we call that N. N is 1. That stands for the width of the rectangle. So, if the base of my rectangle is 1 unit, I have to come up and get the right rectangular approximation of the first. So the top right corner of the rectangle has to be on the curve. So come all the way up to the top right of my rectangle is on the curve. My second rectangle, again, has width 1, and it stops when the top right corner hits the curve. And 2 more. That makes sense on the top right corner determines how high the rectangle is. Is this, if we do the area of those 4 rectangles and sum them, add their areas together, would this be an over approximation or an under approximation? Okay, why? Because we're adding above the curve that's not actually there, right? So that one would be an over approximation. Okay, pick a second color. I'm going to do, what kind of one? Purple. Now, I'm going to go left on the same curve, so I'm going to go left, but we have different colors, hopefully. Left approximation. So, this is a little tricky. The base of my rectangle is still 1. And I have to take the left endpoint up until it's at the top of the curve. It's on the curve. So how high should I take my left endpoint up? Never. Why is that? Because it's already there. Isn't the left endpoint at 0, 0? So it's a flat line. I actually see the rectangle until I make this one. What is interesting is it shares the right endpoint from the red rectangle. But is it above the curve? No, it's below the curve. On my third rectangle, I go up on the left-hand side, again sharing that same point. But when I cut across the blue of my rectangle, it's actually under the curve. And for my last one, It's also barely under the curve, which means this approximation would be what type of approximation? An under approximation. Okay, let me do a brighter color here. Try orange. If you want to trade colors with the neighbor, you need a third color or get another one out of the box. Third color. Middle. So, again, the width is still 1. The midpoint of that base determines how tall the rectangle is. So the midpoint of the base, if I brought the midpoint up, touches the rectangle right here. And then I go to my rectangle. So it's actually shorter than the red one. For my second rectangle, I find the midpoint. And I come up until I hit the curve. It's right there. Again, it's shorter than the red one, but taller than the purple one. And we do that 4 times. Which estimation do you think is the closest to the actual area? The midpoint. Why? That includes some of the outside, but excludes, I like to use that word, excludes some of the inside, so it kind of balances itself out. Hence, the middle rectangular approximation. Alright, great. Okay, flip it over. We're going to try the different approximations based on what they asked us, and the different widths. So that's what N is the width of your rectangle. Okay, so you can go ahead and pencil and draw this starting with the left. So it means the left endpoint of the rectangle has to be on the curve. How wide is the rectangle? No. 2. The domain is from 0 to 4. That's your domain. This is your width. Okay? So the base of my rectangle is from 0 to 2. How tall is the rectangle only to be? With the left rectangular approximation. The left endpoint has to go to the curve. How high up should I go? To 0, right? It's flat. My next section starts here. From 2 to 4. And I bring up on the left-hand side until I touch the top of the curve. And take the top of the curve to the point and carry your rectangle over. Okay, now we're going to calculate this. F(x). Or approximately, because we are making an approximation. Yeah, 2 rectangles here. And our point is rectangle length times width, right? So essentially, we have L1 times W1 plus L2 times W2, right? With 2 rectangles. But one of those is the same number for both rectangles. What do they have in common? The width is always 2. So I can factor out my W and get W1, which is the same as W2, so I can just call it W, times L1 plus L2. Can I do that? W1 and W2 are the same. Okay, let's plug in. The width is how much? 2. Now, L1 means the height of the first rectangle, which is actually the base. That's of 0, right? So we have 1, and 2, and 3. Let's put 2 and 1. And 4, 5, and 6. So we have f of 0 plus L2. L2 is what? Actually, no, I think it's wrong, didn't I? It should be the values at 1 would actually be right here, right? The height at 1. That 2 would be right here. Of 2. So, for this one, we use f of 2 and we use f of 4. What represents the height of the rectangle? F of 2 represents the left endpoint, right? And like a 0 is the left side of the rectangle. So f of 2. Okay, so we can actually calculate this. We know f of 0 is 0. That's nice and easy. 0. How do we calculate f of 2? How do we calculate f of 2? What does f represent? What does it represent, Christine? Square root of x, the function. So f of 2 is what? Square root of 2. Square root of 2. So we get approximately 2 root 2 is our area. So f of x, our area, actually we should call f of x the function. We should call it LRAM. Just 2 root 2 the area, units squared. Okay, let's try to see the same function but with RRAM. So, in the right endpoint, still with the 2 though. So from 0 to 2, this rectangle doesn't be flat. Oh, but there's the right endpoint, which comes all the way up here. And then the second rectangle comes up to here. So the first graph, is that an overestimation or underestimation? Under, all the rectangles are below. This graph is going to be over or under? Over. So our estimation will be larger. Okay, so RRAM, again, we can factor out the common width. The common width of those 2. And then we just have to add up the right endpoints. So what can I call this right endpoint? In function notation, f of 2. This one's f of 4. So f of 2 plus f of 4. We found f of 2 in the last problem by using a function. So f of 2 was just square root of 2. What's f of 4 going to be? 2, because it's the square root of 4, which equals 2. Okay, so what's our right rectangular approximation? Two root 2 plus 4 units squared. Is that larger than the orange one on the left rectangular approximation? Yeah, mine is the plus 4. So it was larger as expected because it should be an overestimate. Okay, does that make sense? So when you plug in here and here, you're using, in this case, left. F of 0, F of 2. Because this one we use the right. F of 2, F of 4 endpoints. Alright, why don't you just try this one. Determine the area trapped between the curve and the x-axis on a restricted domain from 0 to 4. Notice our width of a rectangle. What's the rectangle width? 4. Okay, your neighbors. Draw out 2. Make sure you know how to draw a rubric. 2 versus the left, that's your approximation for the mid. And two of them together. Well, I don't have that phone going back and forth, but maybe I do. I guess it's like piano. I prefer sharps over flats. It's just flats, just like my brain can function. Most people I think actually prefer flats. I prefer sharps. So I remember in high school summer, there's like 2 years of my piano every day. So to do a lesson on me every day, so finally came upon agreement. And whenever we picked those sharps, I would play those flats, he would play. Also do that, not just drawing it, but actually go calculate the area. And if you're the right hand approximation want to come do on the board for us, make sure you have units. Maybe just slide. That's okay. We'll do it second night. Okay, we use another number 1, the first one. You can go right up the second one. You should be able to write at the same time.
Now we'll really decide which one, whether this one or this one has strong superballs.
Can you just you have to move it too, so don't be over your head. we have an approximation symbol because it is. It is line that means M. Yeah, f of x is the curve that we're approximating here and there. Okay, do you agree with 64 units squared? And 16 units squared? Cool. Okay, I realized, I was like, where are we getting a rectangle? Actually, not really, because they run around rectangles. But we'll do the same one, we'll take back and see what happens when we add more rectangles. If we add more rectangles on this one, what do you think is going to be more accurate? Less rectangles or more rectangles? More rectangles. Obviously that red box that this one that Matthew drew, it was way overestimating, right? So when we calculate the right rectangular approximation width over rectangles, they all end up having the same width, which is 1, right? And all the right endpoints in function notation, do I start with a 0 as a 0 for my right endpoints? No, I start with, this is important because people mess this up, so please listen. Sometimes you use the first point, the last point. When you get in right approximation, you skip the beginning of your interval and start with the next one over. But you have to put the endpoint f of 1 plus f of 2 plus f of 3 plus f of 4. If there's a left approximation, which one may not use? 0, 1, 2, 3, or 4? We're not use 4 because it's on the right side of that last rectangle. We're going to start with 0. We have f of 0, 1, 2, f of 3. Okay? Oops. X squared. So, what's f of 1? 1. We're just squaring it. What's f of 2? What's f of 3? What's f of 4? So we add those up, we get approximately 30 units squared. Is that closer to the actual area? Yeah, it's a lot closer. It's still an overestimate. Yeah, the rectangles are higher than the curve. Same with this one. If we went through and did middle again, is it going to be closer to the actual estimate? Yeah. It's not going to get out on the same function, but how many rectangles do that? How many rectangles do we have this time? 8. So do you think we'll be closer or further away to the real area by having more rectangles now? Probably closer. We're doing one more precise each time, right? That first point there was huge, and we're way overestimating and making 4 rectangles, which is closer, but still overestimating. So, 0 to 4, and we need 8 rectangles. So how wide should our rectangles be? Half. Okay, so 0.5. So that our left rectangle has to start a curve, which looks like it's got to be margin, right? So it's flat. Then at 0.5, we finally hit a little bit of height. And then at 1, a little more height halfway across. And 1.5. That's 2. 2.5. 3. 4. approximation. It's going to be an under. We're missing. We have lots of gaps, right? Let's just look at an interesting relationship. Look at this concavity. Is it concave up or is it concave down? Concave up. Now we're using a left approximation device this way. Concave up, and we're using a left approximation. You said it was going to be an under approximation, right? Let's look at the square root. Is the square root same concavity? Or is it different concavity? It's different. So is this going to be another approximation for left and approximation or over? It's also going to be under. Okay? So depending on the curve, these are both end up being under. But watch out for the different concavities, because sometimes, depending on the curve is drawn, they can switch. Okay, so diagram approximation is approximate. What's the width of the rectangle? We all have a common width, so we can factor it out. Half. Factor it out. And then we write function notation. F of what is our first left endpoint? F of 0, because we're using the left. 0. 0.5 or 1/2 plus F of 1 plus F of 1.5. How many things do we need to make sure we have? 8. What's the last one? 3.5. There's a big parenthesis. Okay? Yes, okay. Now we're going to go and plug in. As a 0, you plug in 0 up here. 0 squared is 0. Plus, what's 1/2 squared? I need a fraction. I think fractions are easier. 1/4. 1/2 squared is 1/4. Right? 1 squared is 1. 2 squared is 4. Plus, what's 1 squared? Did someone say 9? 1. What's 1.5? We're going to go the fractions 3/2 and 3/2 squared. 9/4. Ooh, common denominator. That's so nice. 2 squared is 4. 2.5, you can think of a fraction 5/2. What's 5/2 squared? 25 fourths, common denominator. Very nice. 3 squared, 9. 3.5 squared right there is the packet we're on. And we're on number 3. We're going to go on 2.5, you can think of 7/2, which becomes 49 fourths. So we can add in any order we want, right? Which ones do we want to add together first? 1 and the 9. 4. Whole numbers. So how much is that? 14. That's a fraction. 9 plus 9, or 1/4 plus 9/4. 1 plus 9 is 10. So use your calculator. Let's put that in one calculator. 10 plus 25 is 35. Okay, careful. 35 plus 49. So back out nicely. And the 8 4 divided nicely. 21. So 14 plus 21 has to we're the approximation symbol going. 14 plus 24 is 35. Which is what? Approximately 17.5. You can leave as approximately 35 units squared. Is that allowed on the calculus test? Yeah, mathematically equivalent to decimal form. Okay? So let's get what we started with the same function, just adding more rectangles. We did the one rectangle, we got 64 units squared by right approximation. Middle approximation, we got 16 units squared. Interesting, 16. That's quite a jump from 64, isn't it? Okay. When we did 4 rectangles, we got 30. Also quite a jump from 64. But closer to what we got here. That's 16. That was pretty damn close. That was the closest one, wasn't it? And we have more rectangles. What if we did 100 rectangles? Would we be getting closer to the actual area? 1,000 rectangles. 1,000,000 rectangles. Let's do that. That's why we have calculus. Because there's a way to do it. But we're not going to learn that quite yet today. Alright, with your partner next to you, we'll do number 4. A and B. Remember? Since your closed interval, number of rectangles, and I'll put up earlier. So there's going to be 3 rectangles. How wide are they each of the rectangles? How wide does it have to be? 2, because our interval length is 6 divided by 3. The width of the rectangle is 2. Okay? And again, I'm going to talk about your topic 6 homework section. Okay. Okay, about another minute and a half, and then we're going to skip to number 5. Okay, the first one, you all got 80 units squared, right? Okay, good. Okay, I'm just making everyone clear. Okay, this one and a 6 and a width of 2. With the midpoint is when x is 1. And then an x midpoint is here. And 6 is right here is when you stop. So when you set it up, and ram, can't tell. You ready? Doesn't seem like it. It should be f of what? Good. Use the midpoint numbers. F of 3, F of 5. And then at the end, we're getting 74 units squared. Do something else. Question? Okay, come over to number 5. My school calculations are what you put in there. Oh, decimal place. Oh, because we have symmetry, right? That's one. Okay, remote control cars velocity was recorded. Estimate the total distance driven within a given time frame. And take some values over there. And then a brief chart. So what should you do? Follow that, yeah. 0, 1, 2, 3, 4. Actually, it looks like I don't have enough dots, so we should probably consider the empty. The highest one is 8, and then I have 1, 2, 3, 4, 5 dots. So I should be counting by 2s. So if you do 1, 4, probably will have 2 dots. 3, 10. Oops. And then 2, 6. 3, 10. 4, 5. 5, 7. 6, 5. 7, 10. 8, 8. 9, 7. And 10, 9. Okay, we're seeing number 5. I have this packet. Okay, right rectangular approximation. 10. So what's the width of each rectangle? 1. Yep. So approximation, width of 1, we come up with the right side, and the height of 4, right? sounds totally out, but set them up. Right rectangular approximation. What's the common width we can factor out for all of our regions widths? What's the common width of each rectangle? 1. Then we need to find f of what value? F of 1. Do f of 0, do f of 1. Plus f of 2. What's the last one? F of 10, because that's the right side. Yeah, okay, let's go to the other one. We're not going to draw it, but how wide should this rectangle be for part B? 2, because we need 5 rectangles from 0 to 10. So 10 divided by 2, or 10 divided by 5, so this will be 2. Okay, what's the midpoint of the first rectangle? F of 1. Plus, what's the midpoint of the next one? F of 3 plus F of 5. So all the odds, right? F of 7 plus the last one is F of 9. And their heights will be obvious because they're all virtually photographs. Okay, so your homework on this purple sheet. Let me make sure I get you one. 6.1. Tell problem number 9, and it's 6, so you need 6 rectangles. Problem number 10, and it's 4, etc. So 9 through 12, you have two of the problems. You can left ram, right ram, or end ram for each. And 2 of the problems, so 9 through 12, 9, 10, 11, 12. There's 4 problems total. You need to, on 2 of those problems, do the left hand approximation. On 2 of them, you need to do right hand. On 2 of them, you need to do middle. So we can choose. Does that make sense? Okay. And then the other 2. Left and right approximation. Number 10, you do left and middle. You right on the left twice, so you're covered there. On number 11, you have to do another middle and another right. And in the last problem, you can choose what you want to do. Does that make sense? So between the 4 problems, you do a left ram twice, a right ram twice, a mid plate twice. And the other one is optional, whichever is your favorite.